So I have a webcomic called Linalg Library, and they're up on my website called linalglibrary.com, and I have 8 episodes up there. And while my math friends enjoy it, some people have told me that it's hard to follow, which is fair. There is some college level math in there. So this is a simplified commentary. I'm going to sacrifice some rigor so that more people can actually understand what's going on, though I know some of my math friends might be dismayed. But anyways, here we go. What if numbers were characters in a universe? Linalg Library is a story about the number 3 traveling through the mathematical multiverse. Welcome to Universe, the universe of integers. The Z in the middle is the symbol for integers, and it kind of looks like a slanted eye. As you might know, integers are a set of positive and negative numbers and 0. The integers don't include any fractions or decimals. He is having a good old day until 6 shows up. 6 is a perfect number. What's a perfect number? A perfect number is a number whose prime divisors add up to itself. For example, 6 is prime divisor, that is, prime numbers that divide 6 are 1, 2, and 3. Surprisingly, if you add all of them up, it's 6. Such numbers are called perfect numbers. Here's a fun fact. All the perfect numbers discovered so far are even numbers, which made people suspect that there is no odd perfect number. But for more than 2,000 years, no mathematician was able to prove that there isn't one. But 6 here just faultily assumes that odd numbers can never be perfect. So 6 hates 3 and is about to stab him with some trident. Actually, that trident is called a homomorphism. What is a homomorphism? If you strip away all the rigorous language, imagine one group of things and then another group of things. A homomorphism is a rule that links every single thing in the first group to something in the second group, but it's not just random matching. It preserves relationships. For example, let's say our first group is the integers. We take 1 and 3. When we add them, we get 4. Now a homomorphism sends 1 to its equivalent version in the second group, 3 to its equivalent version, and 4 to its equivalent version. And here's the key. The relationship is preserved. So in the second group, when we combine the equivalent of 1 with the equivalent of 3, we get the equivalent of 4. Whatever relationships exist in the first group can be replicated in the second. So basically the trident here maps 3 to its equivalent version in another mathematical universe. In our case, that universe happens to be the set of 2 by 2 matrices, and 3's equivalent version there looks like this matrix. We can read it like the matrix with the rows 3, 0 and 0, 3. But I'm getting ahead of myself. What's a matrix? A matrix is just a table of numbers. A 2 by 2 matrix means that it has 2 rows and 2 columns. Matrices is just a plural of matrix. And look who 3003 meets. Matrix Man. Matrix Man says, "Holy moly, you fell from the sky. Where in vector space did you come from?" A vector space is basically a setting where vectors live. That's not perfectly precise, but it's a helpful way to think about it. Just like integers live on a number line, vectors live in a vector space. But what's a vector? Well, think of it as an arrow on a plane. It has a length, called magnitude, and a direction. For example, the vector 1, 3 means that it goes 1 step right and 3 steps up, because right is usually the positive direction, by convention. 1, 2 is 1 to the right, 2 up. -1 and -3 is 1 to the left and 3 down. Matrix Man shows our friend around, and he introduces him to the vector vendor. And this guy basically sells vectors. And this guy shows us how to multiply a matrix by a vector. So take this matrix, 3, 2, 2, 3, and this vector, the vector 1, 2. When we multiply them, we get 7, 8. This is called matrix vector multiplication, and this is how it works. We first take the first row of the matrix and turn it into a column. And then we multiply the corresponding numbers and then add them together. And that becomes our first element of the vector. We do the same with the second row. We flip it, and then we multiply them and add them, and that becomes 8. This process of multiplying the corresponding numbers and adding them all up is called the dot product. So basically, matrices in this universe can act on vectors to create new vectors. In this world, the transformed vectors are used like zip lines that let people travel through vector space. For Matrix Man, this is especially convenient because he can become any matrix he wants. He's literally the general matrix, meaning the 4 entries in this matrix A, B, C, and D can be any integer. But our main character doesn't care much about vectors or zip lines, he just wants to go home. Matrix Man then realizes that the main character doesn't really belong in this universe and offers to take him somewhere that might help. Together they ride down to the Eigen base through the Eigen Vader. Eigen is a German word meaning own or self, and it shows up everywhere in linear algebra. Basically, an eigenvector of a matrix is a non-zero vector whose direction does not change when the matrix acts on it. The vector might get stretched, shrunk, or flipped, but it still points along the same line. The amount of stretching or shrinking is called the eigenvalue. For example, take the matrix 2, 0, 0, 3, and the vector 1, 0. When we multiply them, we get 2, 0. Notice that the vector still points in exactly the same direction. It just becomes twice as long. That means 1, 0 is an eigenvector, and the eigenvalue is 2. Eigenvectors are considered intrinsic or special because they reveal directions that the matrix naturally preserves. Most vectors change direction when a matrix acts on them, but eigenvectors keep theirs. So what's going on below the eigenbase? The general idea is that deep below the vector void lies a source of integers bubbling upward into the void. Inside the void, integers pair up to form vectors. Then giant pipelines connected to the matrix cubes suck the vectors upward, where collections of vectors are assembled into matrices. Make sure to like, comment, and subscribe if you like this video. Also, if you want to see more commentaries like this for my other comics, let me know in the comments below. And if you want to see my other comics, they're on linalglibrary.com. Please check them out if you're interested.